Well, hello everybody. I should say, first of all, I would like, of course, to thank the organizers of, being so brave to organize this conference in this hybrid form, if it goes through. And second, I should say that it's also a very interesting experience to do the talk almost 2 months before the conference itself. But nevertheless, let's proceed with it. First, I should say that I completely changed title from the last year one, well, because time is passing and because also my first title was too broad to be able to explain everything in this short time. But this is also one of the most interesting at the moment mechanisms of the magnetization reversal, what I want to talk about today. First of all, I would like to thank my co-workers for, well, doing the job actually. People from Nijmegen and Delft in the Netherlands, Białystok in Poland, Stuttgart in Germany, but also the team at the Felix Free Electron Laser allowing to do these experiments. So what are we talking about? There are nowadays many recipes for ultrafast switching of magnetization with laser pulses. This is, of course, the famous materials such as gadolinium, iron, cobalt, but then few others, terbium, cobalt multilayers or Hössler alloys based on manganese. A single shot with a laser reverses magnetization due to ultra-fast heating of the sample. Very simple, sounds very simple, but it's really a rather complicated mechanism based on the exchange between ferromagnetically coupled sublattices. On the other hand, in ferromagnetic multilayers, one can switch magnetization depending on the helicity of the laser pulse, but you need to be slow and use many pulses. Third, what I would like to mention here, which is maybe most interesting, is so-called cold switching, where temperature of the sample is hardly increasing, less than 1 Kelvin in this experiment, but magnetization nevertheless reverses depending on the polarization of the incoming laser pulse. And you can switch it back and forth in just 10-20 picoseconds because temperature is not an issue here. So the question for this talk is, can we find another non-thermal approach to the magnetization switch? Well, as I will show you, this is related to phononics or acoustic system of the crystal. It has been shown already a while ago that such strain pulses can affect the magnetization. For example, if you launch a strain pulse here from the back of the substrate, when it reaches magnetic semiconductor layer, gallium manganese arsenide, it affects the magnetization, it changes the anisotropy, and because of this, it launches precession. And based on this result, there were proposals that if actually this acoustic pulse, this strain pulse can be made strong enough, then it should be sufficient to switch magnetization, and depending on the pulse widths and strengths, you have different regimes when you switch back and forth between different equilibrium directions of magnetization. So how should we proceed here? Well, we start from far away. I just should remind you that if you want to excite matter to large amplitude, then resonance is an option. Like this unfortunate breach recognized when winds just shaked it to such amplitude that it broke entirely, and this was the end of it. Just because of the resonances. However, what we would like to do here is to use such resonances for a constructive effect, not a destructive one. How do we do it? Well, what do we need here? We need a strong pulse of the strain in the sample, and we can generate it using nonlinear phononics. To explain you what it is, I remind you about this very old experiment. You take a pendulum mass on a stick, on a hard stick, and normally it would be just oscillating in normal direction downwards. But if you start shaking its suspension point very fast, then in fact such pendulum will obtain opposite to the original equilibrium direction, upside down. And it can make a slow oscillations in this upside down position. Yeah. Moreover, if you shake it strong enough, then the downwards equilibrium direction is not an equilibrium anymore. So you remove this position and you create a new equilibrium. The same can be done with crystals and phonons in them. It has been shown, mostly developed in the group of Andrei Cavalieri in Hamburg, that if you excite an infrared active phonon mode to a large amplitude, then orthogonal coupled Raman mode will have a shift in its equilibrium position. So that means for an optical phonon, that means that, well, interatomic distance changes without actually changing the volume of the unit cell. They develop it further, they calculate it for different materials, and you see that in some cases you have shift of equilibrium, in another case you have a creation of the new equilibrium, so that original one is not an equilibrium anymore, exactly like with this Kapitsa pendulum. Can we use this? Well, let's try. For the samples, we will take cobalt doped yttrium iron garnet. Structure is very well known. This is one of the most known magnets, probably. Presence of cobalt in the sample is responsible for rather strong cubic magnetic anisotropy with equilibriums around diagonals. So you have 8 different equilibrium directions in this sample, which leads to quite complicated domain structure. An optical absorption here is also very well known. You have a band gap below 2.5 electron volts, and you have optical phonons at much lower energies. So how can we use these phonons to switch the magnetization in the sample? Well, you need a light source for it to start from, because the phonon frequency is not what standard laser will give you. And here we use a free electron laser for infrared experiments called Felix for short. And in fact, just to mention, this is the international user facility where I am working now. And if you are interested, just look at the rules and apply for beam time. It's freely available to any users. Okay. So we have full tunability between about 3 micrometer and 1.5 millimeter wavelengths, or between 200 gigahertz and 90 terahertz if you want. And we have several tens of microjoules in a single picosecond or even shorter pulse. That should be enough to switch magnetization. Well, it's not entirely true. The time structure of free electron lasers are not always very convenient for such experiments. You have pulses coming in bunches or macro pulses, and inside of bunch you have these very short pulses but following at rather high repetition rate. So for this we use a pulse slicing scheme, just to take a transient mirror and take just a single pulse out of the bunch. And in fact, we managed recently to demonstrate that we can do cavity dump of one of the lasers, extracting pulses with an energy up to a couple of hundred of microjoules, which is huge energy considering that the photon energy is probably 20 to 30 times less than the usual photon energy of the visible laser light. You have a lot of phonons in one pulse. That's sufficient for anything. So we have a sample, we have a laser, and we do a very simple experiment. We take the sample, we saturate magnetization in one of the equilibrium direction, here number 8, around this diagonal, and we just shoot a single micropulse onto it and see what happens. And what happens is that the pulse generates a very interesting pattern. Nothing happens in the middle of the pulse, where the intensity is the highest. But on the sides, you generate this 4-domain pattern, and the direction of magnetization in these domains is shown here. So you generate kind of orthogonal directions, 1 and 7. Look at this picture to see. what it is. And in fact, you notice that if you rotate the original magnetization direction, then the whole pattern rotates with it. Yeah, so this is number 8, this is number 1, and you see it rotated. This is number 7, number 2. You just generate very similar pattern, but just rotated or reflected or change contrast. So what happens here? First, you notice that if you shoot second time or if you shoot 10 pulses, the picture is the same. First pulse switches, and then the rest do not do much. Yeah, you can shoot many pulses. Second, you try to understand what the hell is going on at the center. The maximum intensity doesn't make much change. Yeah, so this is the center of the pulse here. Distance from the center, nothing happens here, but the area switches where the gradient of the intensity is the largest, and only in the direction perpendicular to the original magnetization direction. If you change the intensity of the pulse, clearly at low intensity nothing happens, and then the pattern grows in size, and eventually you enter this sample damage regime, which you really don't want to reach. If you look at the spectrum, if you change wavelengths, then you realize, well, there are lots of phonons in this sample. Magnetic unit cell contains 80 atoms, so you can count yourself how many phonons we have here. But you just measure using spectroscopic ellipsometry phonons in this range. You have transverse optical phonons that are given by the maxima of absorption, or you have longitudinal optical phonons given by the inverse of the epsilon, inverse of the dielectric function. And then you figure out that somehow this strong absorption at TO phonon doesn't do anything, but excitation of LO phonon, though very well ineffective as it should be, creates this magnetization pattern and results to switching. So this is very good correlation between them. When you have a longitudinal phonon, you have switching. When you have transverse one here or there, you don't have it, period. Well, we try to pump harder at transverse optical phonon, saying it must do something. Well, it does something. It leads to appearance of these very small domains in the center, demagnetization if you want. And if you pump harder, you come to the structural damage of your sample. And maybe one interesting point, the cracks are really following the crystallographic axis. This is 001 oriented sample, so you have square pattern, and we burn many triangles in 111 oriented samples. So this is maybe not about magnetism, but nevertheless interesting result. We tried to understand the time dependence of this switching, but we could not do it at our laser. We went to our colleagues in Delft that had an optical parametric amplifier on the shortest on this wavelength range. They do see precession induced by this laser. Precession has maximum amplitude exactly at the same 14 micron wavelengths where the LO phonon is sitting, but more than that we cannot say here from this measurement. Then what happens? Why LO phonon is here? Well, first of all, in thin garnet film, perpendicular to the plane of the film, the usual inversion symmetry of the crystal structure of the garnet is broken because of the growth. So you say the oscillations along this direction have most unharmonicity, and because of this, they have the strongest interaction with other phonon modes, and because of this, they lead to more macroscopic crystallographic strains because of this. That's the only what we can assume here so far, and I'm telling you that this problem has not solved yet. There is still question mark. What is exactly the role of this longitudinal phonon? We shouldn't be even excited as in ideal case. It's sort of inductive excitation. There is no absorption at this frequency. Okay, second, how can we explain the pattern? Well, we took, well, simple formulas for the radially symmetric strains, where displacement for the Gaussian will be calculated to be given by such formula. Then we put it into induced strains in this. Then we calculate magnetoelastic energy that contains this symmetric part by the first term and antisymmetric part by the second term. And we put it into micromagnetic calculations. And then we see that if we put it in here, we do a shot and we get 4 domains. Yeah. Can you understand it maybe on a simpler level? Well, very trivially, you have a Gaussian pulse and you have magnetization directed along a diagonal. Then, because of this, the Gaussian pulse, you have some sort of, well, think of trivially expansion. Okay, that creates radial strain. Nothing happens in the center of the pulse, it's symmetric. But strains on the sides create extra magnetocrystalline anisotropy, which is directed radially. Along the magnetization line, nothing will happen because magnetization is already happy. Perpendicular, you have maximum torque. But exactly perpendicular to the magnetization, you have unstable equilibrium. Yeah, you are seated on top of the hill. That means that left and right from this unstable equilibrium, you go one way or you go another way. And the same here. So you create 4 domains just because of this radially distributed excitation. And this is really a pattern that proves the mechanism of this excitation. That's how we can understand it. How can we understand sequential pulses? Why one pulse produces these and second pulse doesn't do anything? Well, you can try to simulate it. It's not very difficult. You just put it back into micromagnetic simulation and you see that first pulse indeed creates these domains. And second pulse, well, it excites it again. Maybe domains have grown a little bit, but nevertheless, they're still there. They did not change much. In principle, they are the same. Okay, and this is the idea. Then, question is it the only sample showing this? Well, no, of course not. We just took another garnet, grown in another place with different compositions, with totally different anisotropy, or better said, hardly any anisotropy. It's extremely soft garnet. It's extremely soft garnet, almost no anisotropic ions. And then we put a slight magnetic field into the plane of it, and then we just rotate the same crystal, and these are patterns generated. Yeah, you still have the same kind of 4 typical domains here and there, here and there. In some cases, you generate even more domains than 4 somehow. Pattern changes, but characteristic stays in the center, no domain, and then those domains growing from the center. Okay. Here we could do even better. We finally learned something, and we try to see how these domains appear in time. We should still analyze this a little bit, but if I show you, you see that the first domains, they basically have, well, 0 time means instantaneous to the resolution of our experiment. But our resolution, we image this with neodymium YAG laser with 5 nanosecond pulses. So this is our resolution. But what you see after that is that domains evolve as stripes. And these stripes just propagate from the center, going to larger and larger distances. Okay. And so in a time scale of a couple 100 nanoseconds, I think I forgot to put, it's about 100 micrometer, the size of this image. They go to maybe 100 micrometer. So the speed of this propagation of this pattern can be estimated by a few 100 meters per second, which is rather corresponding to the magnetic waves, to the magnetic domains, and a bit slow for the elastic waves as such. However, it could be that these are coupled magnetoelastic waves that propagate, but they are not at small amplitude. These are 180-degree reversed domains that we observe here. This is nothing like small precession and magnetostatic waves propagating. These are really very large amplitude excitations propagating from the center. And finally, as you see here, forming this 4-domain pattern. Okay. Before concluding, something else about phonons. Well, you know that I love the sample called gadolinium iron cobalt. So what I do now, I go back to it and I try to reverse magnetization in it again with the infrared light, but using old method. As in our very first paper, we just take a sample with domains and we scan circularly polarized light over it. Yeah, we know that in principle, formation of domains here is rather artifact due to the magnetic circular dichroism, but nevertheless, effect is very clear and easy to measure. And then we do it with different wavelengths of the excited light. And we see that in some cases, well, this is quite helicity dependent. In some cases, it doesn't depend much on the helicity. And if we plot spectrum of this effect, we find that this spectrum exactly corresponds to the spectrum of TO phonons in the substrate. This is silicon oxide substrate, fused silica. And the phonons are rather sharp in it. Yeah, and we see that switching exactly correspond to that. Well, we try to calculate, maybe there is some unusual reflection from the silica in this range, from the fused silica in this range, and we have more intensity in the magnetic field. No, it's just opposite. Because of the strong absorption in fused silica, there is much less intensity in the magnetic field. Why does it reverse? Well, there was quite some work about circularly polarized phonons, mostly theoretical, but they show that in fact there are phonomagnetic analogs to optomagnetic effect instead of inverse Faraday effect based on electronic excitations. There is the phonomagnetic effect based on the phononic excitations, and because phonon excitations live much longer and have much longer coherence time, it can be that this phononic excitation leads to much higher effective magnetic fields. And this is this phononic excitation in the substrate that really helps reversing the magnetization of the magnetic film itself. But this is still something to be studied. To conclude, I think we can clearly state that we do observe phononic switching of magnetization. We pump optical phonons and we see the permanent effect of magnetic switching. And the spectrum is clear. These are longitudinal phonon modes that are responsible for switching. And I think the observed 4-domain pattern also proves the strain-induced mechanism. I thank you very much for your attention.